All right, in this video, I continue section 3.3. As you remember, section 3.3 is about writing linear systems of ODEs using matrices. And last time in the previous video, I defined the superposition principle for homogeneous first order system of ODEs, the linear system of ODEs. And that superposition principle has linear independence as a condition, right? So now let me start with what linearly dependent and what linearly independent is, okay, in this video. Okay, a set of n vectors is linearly dependent if there exists a set of complex numbers, a1, a2, a all the way through an, and at least one of which is non-zero, such that a1 x1 plus a2 x2 plus all the way through, there's a plus sign here as well, an xn is equal to 0, okay? And it is linearly independent if the above equation is true, and the only condition to make it true is just having the zero coefficients, okay? Then it's called linearly independent. Okay, so let's look at the examples. Maybe it will be easier to understand with the examples. Determine whether the following pairs of vectors are linearly dependent or linearly independent, okay? So this is our first vector and second vector. And when I look at the vectors, I can see that if I get 2x1 plus x2, right? 2x1 will be 2, 0, plus x2 is negative 2, 0. So it is 0, 0, right? Yes. So we get the 0, 0 vector as a linear combination of these guys, and the coefficients are not all 0. That's why this is linearly dependent, okay? By the way, I can look at the determinant of the matrix obtained by these columns, okay? 1, 0, negative 2, 0. If the determinant is 0, it's also linearly dependent, okay? And if you look at here, determinant is 1 times 0 minus negative 2 times 0. So it is 0. So having determinant equal to 0 also shows that they are linearly dependent, all right? But if you look at this example, the next vectors, they are quite simple, but I'm just switching the position of negative 2 in x2, right? And when I look at these vectors, I cannot come up with a linear combination easily. So let me write a general linear combination, okay? So a1 x1 hat plus a2 x2 hat will be equal to, right? a1 x1 will be a1 0 plus a2 x2 will be 0 negative 2 a2, and that's equal to a1 negative 2 a2, and that's we want to make it equal to 0, right? And the only possible way to make it equal to 0 is just setting a1 and a2 equal to 0, right? So this implies that a1 is equal to 0, a2 is equal to 0. So the only way a linear combination of these guys equal to 0 is those coefficients are 0. So this is linearly independent, okay? But again, I can use the determinant of the matrix constructed by these vectors, 1, 0, 0, negative 2. And the determinant is 1 times negative 2, 1 times negative 2 minus 0 times 0, 0, which is negative 2, which is not 0. So it is also enough to show that these guys are linearly independent. All right? Okay. All right, let's move. Okay, how can we solve non-homogeneous first order linear systems. Again, as I said in the previous video, it is very similar the way we solve the non-homogeneous first order equations, okay? First order differential equations. So let's look at this theorem. We have x prime equals px plus f. Let's say this is a linear system of ODEs. Suppose x sub p is a particular, one particular solution. Then every solution can be written as, you remember, x sub c plus xp, where x sub c is the solution of the associated homogeneous equation, all right? So this, again, as I said, very similar with the one equation case. And similarly, we can also define initial value problems using vector equations, okay? So we can have such a first order linear system, and with addition that, we can also have an initial condition, and I can rewrite initial condition this way, okay? So let's look at this example. x1 prime is equal to 2x1 minus 3tx2 plus sine of t, and x2 prime is equal to e to the t x1 plus 3x2 plus cosine of t. And initial conditions are x1 of 0 is equal to 4, x2 of 0 is equal to 1. Let's rewrite these guys in this vector equation form. Okay, so okay, what is, maybe I can start with again x prime of t is equal to, what is p of t? P of t, just look at the coefficients of x1 and x2, right? 2, negative 3t, and e to the t, 3 times x of t plus, and f of t is this part, right? Sine and cosine. Sine of t, cosine of t. And what is the initial condition? X of, what is t naught first of all? T naught is 0, right? 0 is equal to, again, the order matters. Start with x1, 4, and 1. Of course, in this setup, this is p of t. This is f of t. Okay? So I could rewrite an initial condition problem using vector equation this way. Okay? All right. The one last thing from this section is the similar stuff again with the one equation case. Remember, in the one equation case, we had fundamental solution of a differential equation. And similarly, we call this time fundamental matrix solution, okay? Let's say we have x1, x2, and xn are solutions. And let's make a matrix with these vectors, okay? And let's say that capital X of t be that matrix. We call that matrix as a fundamental matrix solution if every solution to this system can be written as a linear combination of these vectors, okay? And we can also show this linear combination using the matrix, using the matrix notation this time, okay? So this fundamental matrix solution has a set of solution. It is a set of solution, but it has one more special thing, that every solution to that system can be written as a linear combination of the elements of that set, okay? So we call that solution, we call that matrix then fundamental matrix solution. All right, in the next sections, 3.4, we are gonna work on how to find fundamental matrix solution of first order linear systems. But for now, let me stop here.